Hey, you guys. Well, here's our second half of Chapter 8. Normally in lecture, in a normal semester, we take two lecture periods to talk about Chapter 8. There's a lot in here as far as the periodic relationships of, of the elements. I always love the historical pictures in here. I always forget who this guy is. This guy is, I think, the one who discovered the noble gases. But anyway, let's go on and continue on with Chapter 8. We're now discussing more characteristics or descriptors of the elements of the periodic table. One of those is ionization energy. Ionization energy dictates how easily an element, an atom of that element, forms an ion, a positive ion. Ionization energy is the minimum energy required to remove an electron from a gaseous atom. So ionization energy, it's endothermic. You see it right here. It's on the left side. So energy goes into this atom, and that electron is kicked out. This is a positively one-charged cation that was just created. That would be called the first ionization energy. The second ionization energy is the amount of energy required to remove the second one. And then the third to remove the third, and so on. So to remove all of them, you would just add all of these together. Now, the very first ionization energy is usually is lower than the second, which is lower than the third. And this is a result of the increased attraction for the remaining electrons after an electron is removed. So our first one up here was neutral. This is positive. This one was +1. So the remaining, but the protons did not change. The protons were the same for every one of these atoms. So the proton to electron discrepancy was increasing. So the protons were really holding on to the remaining electrons, and that's why the ionization energy was increasing. So as far as the size is concerned, if X was this size, the size of X plus 1 is smaller and then smaller. Remember, the cations get smaller as they lose electrons. So this table out of your textbook shows the first, second, third, fourth, fifth, and sixth ionization energies for selection of elements. If you just check out the trend, you can see that the first ionization energy is always less than the second, is always less than the third, is always less than the fourth. Now, what's odd is that you do see some jumps, some really big jumps. This 899 for beryllium to lose its first electron, and then about 1700 to lose the second one. So it's almost double. But then we go to much more than double. And when you see this occurring, it's because the amount of energy needed is so great because you're trying to break into the noble gas core. Beryllium is an alkaline earth metal, and his electron configuration is 1s2, 2s2. So the first and second electron are not too bad to lose, but then when it wants to get into the noble gas core, that's when you see the jumps in the amount of energy required. So if I choose any element on here, say fluorine, for example, and I go first, second, third, fourth, fifth, sixth, I don't know, they all look kind of the same to me. Where was there a situation where it was trying to get into the noble gas core? Well, let's write the electron configuration. 1s2 for fluorine, 2s2, 2p, I believe it is 5. So it would have to be getting the sixth. So I don't know, there's a jump here of almost 5,200. So I guess that is a bigger jump than some of these other ones. And another example of this, look at phosphorus. Phosphorus, he's going along okay, he's losing, and then here's a big jump, and then here is a huge jump. So that would be the sixth ionization energy for phosphorus. 1, 2, 3, 4, 5, 6. So that was getting into the neon noble gas core when you were trying to do that. So the ionization energy is a descriptor of the elements that shows how easy or not easy it is for an element to lose an electron. If you look at the noble gases are quite high in reference to metals. Metals have much lower ionization energies here. Here is a metal. A metal, they have quite low comparatively. So here's sodium, is pretty low. Potassium's pretty low. That's because they like to just lose, they can lose that one, and that's okay. But as soon as you try to get into the second one, these are all alkaline earth metals, they do not want to lose that second one because you're trying to get into the noble gas core. So again, one of these funny graphs, just overall, there is a trend as you go from left to right on the periodic table that ionization energy increases. Ionization energy increases as you go from left to right. Ionization energy also increases this way. As you go from bottom to top in the periodic table, you're getting closer to the nucleus. So remember, we have shells down here. And then we go closer, and then we go closer, and then we're even really close. The ionization energies just get so high because the protons in here are attracting it so much that it doesn't want to let go. As far as going from left to right, we're increasing our ionization energy because we're increasing our number of protons. Yes, our number of protons. We're also increasing the number of electrons, but you get to a certain point in the periodic table that it's easier to gain to get to a noble gas than it is to lose, and that's why you see this general trend. So let's look for a trend from left to right. Here we have lithium, and then where is beryllium? Beryllium is number 4. Here it is. This is row 2. From left to right, ionization energy increases. Left to right, ionization energy increases. You can see it throughout. You get some weird things in here, and that's because of your transition metals, and it's also because of some available d orbitals that are there. And these are the different rows that I was just showing. 4, and then do we have a 5? Yep, this is row 5. From left to right, increasing. So your general trend then is from left to right, you see an increase in ionization energy, and from bottom to top. So as a quiz here, if we have 2 atoms, those 2 atoms, one has an electron configuration of 1s2, 2s2, 2p6. The other one is 1s2, 2s2, 2p6, 3s1. I'm thinking this is sodium. I'm thinking this is neon. Which is which? 2 atoms, 2 ionization energies. I think this one must go with that. And they must be talking about the first ionization energy here. And then this one goes with that. This one is breaking into the noble gas. This one is not. Now, electron affinity is like the flip side of ionization energy. It's the negative of the energy change that occurs when an electron is accepted by an atom in the gaseous state to form an anion. I know that sounds kind of like Greek, but this is just saying that F, like fluorine, if he's by himself, he's not F2, he's just a fluorine atom, and he's a gas. He does like to gain an electron for sure to become fluoride. Very common. Because fluoride would much rather be reduced than oxidized. So when we say that the electron affinity is the negative of the energy change that occurs, there's an energy change that occurs right here as an enthalpy, and it is negative. Negative means exothermic. It means it's going down to a lower energy state. But electron affinity is just taking a negative of that negative number. It makes it a positive. And then when we put numbers for these electron affinities to the elements on the periodic table, then you can see a trend. There's that number. There's the electron affinity that's now made positive. So oxygen, there's a number, exothermic, because oxygen doesn't mind gaining electrons and actually wants to. That's why you have this negative. The electron affinity is defined as the negative of that. Now, looking at these 2 numbers, what does that indicate? If this electron affinity is higher than oxygen's, that means fluorine has a higher electron affinity than oxygen does, and that is true. So that's why they put the negative of the negative on there, because then it makes you be able to see the trend. There's an increase in this number. This table is a table out of your textbook that shows that. You have, as you go from left to right, there are some trends here, but they're kind of general. So left to right, you have an increase in electron affinity. Now, it's kind of general. It jumps all over the place because, look, you have 60 of an electron affinity, then it goes down to nothing. Then it goes up to 27, up to 122, then down to nothing. then it goes up to 141, then up to 328, then down to nothing. And the reason for that is because of the electron configuration. You have to look at that specifically and individually to see where that electron would be put, and if it is favorable to be put there at all. Nitrogen doesn't really want to have any electrons. He will, and he's stable once he gets them. But remember, nitrogen has an outermost electron configuration of 2p3, and those guys don't want any partners. Once you put the first one in, and then put them all in, then that's stable. But to overcome that repulsion in the beginning is rough, and that's why it goes down to 0. There's a couple strange ones here. Less than 0, beryllium. Those have already full S shells. So in order to do that, you'd have to put it into a P, a 2p. Same thing here. Calcium starts to get a little bit more, and I think that's because the empty shells or empty spaces are so far away and there's less repulsion. Neon, much less than 0, again, because they're all full. Nitrogen, we just talked about on that one. So how would we say this? The more negative or positive the electron affinity, the more favorable it is to gain an electron. It's the more positive. So that's why this guy's very positive and this one's positive, because they really like electrons. So I'll let you guys play around with Funchy question number 9. We just talked about the periodic trend on the previous slide. To write an equation representing an electron affinity, remember you just have your substance, and then it gains an electron to make whatever anion. The delta H for that should be negative if you write it this way. Now, given our description or definition earlier, since electron affinity is the negative of, you might also see it written like this. So I'm just flipping it. And now your delta H for this is a positive number. So now, looking at this question about sulfur, remember I said look at the individual electron configurations and see how likely it is that sulfur would want to gain an electron, and if he did, where would he put it? Now the last half of this chapter is just pure fun. It's just looking at the elements, looking at the groups, and then seeing what they do and what they look like. This is called descriptive organic chemistry. And it's almost like being a medical student, because you can explain some things, but a lot of times you just have to memorize everything. So we are going to memorize what the alkali metals do. They form positive 1 charges. They like to react with water explosively, as we know, to make hydrogen gas. And they react with oxygen to make oxides in this ratio. Because remember, M becomes positive 1, oxygen's negative 2, and that's why you get this formula. So as you go from top to bottom, you will get an increase in reactivity of the alkali metals. That's because your electron in cesium is much further out. Remember, our numbers here, our quantum numbers, would be 1, 2, 3, 4, 5, 6. So in cesium, his 1 valence electron is way out here and is not paying much attention to the nucleus, so it's very easy for it to be lost. How about group 2A elements? Alkaline earth metals, they like to form positive 2 charge. They do not react too much with water. Some do though, but you might have to have it in the gaseous state. Now for liquid water, looks like calcium will react with liquid water. These need some more energy, and this one doesn't react at all. So the alkaline earth metals, calcium, strontium, and barium, will react with water readily to form the hydroxides. So that's why these are called alkaline. Alkaline means, sorry about my writing there, means basic. And a basic solution is something that has hydroxide in it. And that's why alkaline earth metals and the alkali metals also made basic solutions. Again, increasing reactivity as you go down for the same reasons we discussed on the previous slide. Group 3A, boron, aluminum, gallium, indium, and thallium. They're all metals. They also, but then we get into some, boron is a metalloid, aluminum is a metal, and all of these are metals here. Aluminum can react with oxygen to make an aluminum oxide. That's what's on the surface of your aluminum foil. It's hard to get aluminum to react sometimes because it's got this oxide stuff on the surface. But when you do get it free, it does react with an acid solution to make hydrogen gas, just like the others. Group 4A elements, carbon, silicon, germanium, tin, and lead. They also react with acids. Group 5 elements, nitrogen, phosphorus, arsenic, antimony, and bismuth. They also, now these, we're getting into what's called a non-metal oxide. This is a non-metal oxide. When it reacts with water, it makes not a basic solution like we saw before, but an acidic solution. So this non-metal oxide, dinitrogen pentoxide, will react with water to make nitric acid. Phosphorus will do the same thing. Arsenic can make an acid, and then we start to get into some metals, and they don't act as acidic. There's our phosphorus. 6A, now we're in oxygen, sulfur, selenium, and tellurium. Oxygen's not shown because it's a gas. These, again, are non-metal oxides reacting with water to make acidic solids. Group 7A is the halogens. The halogens are fluorine, chlorine, bromine, iodine, and astatine. Chlorine is a gas at room temperature and pressure. Bromine is an actual liquid. You can see it right down there. And then iodine is a solid. But they don't really have a lot of stickage for each other. So they will easily, you can see iodine gas in here. It's purple. Bromine gas in here. It's red. Chlorine is a gas and it's not a liquid anyway. And it's a green gas. These all undergo, they like to gain electrons. And they also form what's called hydrogen halides. So they will form hydrogen fluoride, HF, hydrogen chloride, HCl, and so on. Hydrogen bromide, hydrogen iodide. And the increasing reactivity is flipped. You notice when we were over here on the metals, we got an increasing reactivity going down. But now it's flipped. Fluorine is more active than iodine and bromine. Finally, group 8, noble gases, completely filled shells, pretty unreactive. They're called the inert gases, and they have the highest ionization energy of all the elements. Now, they don't really form too many compounds, but it was found that xenon would form some compounds. And xenon, you see, is a huge, it's very big. He's way down here. And I think he has some empty orbitals that if something comes along like fluorine, which has lots of electrons, it can kind of plug in here and make XEF4. You'll see that is one of, and XEF2 is another one. Oh, XE, forgot my E. We'll be looking at these in more detail in chapter 10 when we start drawing their structures. So on your fun sheet, there's a question about formation of xenon tetrafluoride from its elements, and there's a picture in your textbook that shows the state of what this should be. See if you can find it. So there's your XEF4. And some krypton compounds have as well. So looking at these groups A and B, see this is a group B. This is a group A. The metals in these two groups have similar outer, could it be electron configurations with one electron in the outermost s orbital. But the chemical properties are quite different due to differences in the ionization energy. So these guys are NS1. This one, this group, which is copper, silver, and gold, these are called the noble or coinage metals. These are, let's look at their electron configuration. If we did copper, it would be what, argon, that in brackets there, and then it's going to be argon 4s2. Oh, is it 4s2 or is it 4s1? Because this is an exception to the rule, 3d10. Because now this is half filled and this is filled, which gives it special stability. So the group 1b and silver, copper, and gold, copper can be copper plus 1, or copper plus 2. Remember, it can do both of those things. Gold is really just, well, gold can be plus 1 or plus 3. And then silver, I've only ever seen it want to be plus 1. So there's probably some electronic stability reasons for that, but either way, you can see why all of these would want to form a plus 1 charge. There he is, Sir William Ramsay. That was the picture on the beginning. He discovered the noble gases and gave them their names too, because helium, neon, argon, krypton, one of these means lazy. I think it's this one. On your fun sheet, there's a question that asks you guys to look up all the individual different substances and try to figure out what description goes with each element.